Alright, let's resume our answering of problems on the applications of first and second law thermodynamics. So we have another problem. Helium is throttled, so we're gonna have a throttler. How do we draw a throttler? I actually don't know. I forgot. Damn. So specific, bro. That's why I couldn't remember it. I think this is the most... What is happening with my stylus, bro? I think this is the most difficult figure to draw among all the thermodynamic devices I have seen so far. And then we have... There you go. So that is a throttler. A throttle, rather. Helium is throttled from 1.2 megapascals, 20 degrees Celsius, to a pressure of 100 kilopascals. The diameter of the exit pipe is so much larger that the inlet and exit velocities are equal. Okay. Required. Find the exit temperature, TE, of the helium and the ratio of the pipe diameters. Ratio. So by default, the ratio is going to be exit over inlet, no? So in this case, ratio of the pipe diameters, I don't know why I wrote A. A is supposed to be area, but that's not area right now. Ratio of the pipe diameters. Okay. We have LCM. LCM is M1. This is steady state. Why? Because there is no mention of accumulation, so we cannot say that this is transient, no? Transient typically tank filling or tank emptying problems. In this case, that's not the case. So okay, so assumptions. There is no mention of kinetic energy and potential energy. We'll discover a few more later, probably. FLT, this is an open system, no? A thermodynamic device is involved. For a throttle, since it's not any of the four that produce or consume shaft work, whatever applies, the shaft work therefore is equal to 0. Okay, so this is open system. So delta H equals Q plus W. In this case, W is 0. So Q is equal to M times quantity H sub 2 minus H sub 1. Let's start immediately at state 1. 20 degrees Celsius, 1200 kilopascal. let's see if we can find something. Eventually later, ratio of the pipe diameters, pressure. We're gonna have these formulas. dE over di is equal to pi over pe raised to 1/2 or square root, no? There's another relationship, a sub e over a sub I equals dE over di raised to 2. We'll worry about that later. For the time being, our gas is helium, no? In this case, since helium is not, there are no thermodynamic, our Sontag table doesn't have helium. So, assume ideal gas, or the gas is ideal. So, if we assume ideal gas, process is reversible and isothermal. So I think 20 degrees Celsius also in the other side. Mm-hmm. Process reversible and isothermal. Since reversible has been mentioned, I think we're gonna also have SLT, no? Our entropy balance. Reversibility has already mentioned, so yeah. Isothermal dt equals 0. SLT delta S equals square root dq over t plus S gen. Q over t plus S gen. Q, we don't know. Entropy generation is 0. Here, Sg equals 0. No? There is no entropy generation in a reversible process by virtue of second law of thermodynamics. Delta S. Okay, so Q, this is Q reversible, no? T delta S. Yeah, there's no need to put mass here since the Q here is already small letter. This is specific heat transfer. That's reversible. Okay, so we can turn this into Q equals H2 minus H1. Simply, yeah, just that. And here, what we can make of these two equations is H2 minus H1 equals T times quantity S2 minus S1. This is the weird problem. Also for a throttling device. Oh wait, no. Not because it is a throttler. Oh no. Mm, okay. So yeah, I have just confirmed it. For a throttle device, it is fundamentally adiabatic. That is, Q is 0. Not because we assumed ideal gas that we say that the process is adiabatic, no? We can say that under isentropic condition, it is adiabatic, but that is not the case here, no? The throttle is fundamentally adiabatic. So from there, hmm, so Q is 0 also. So what do we do? Mm, isentropic, no? Wow. There are two conditions under isentropic. I can't remember the other one. Ah, okay. Reversible. Technically, this isn't wrong. Let's remove all this. So delta H is equal to 0. Here, it's specific enthalpy, no? Because process is isothermal, so yeah, delta H is 0. What are we looking for? Exit temperature of helium. Actually, we already found the first answer, no? This one. We just have to look for the ratio of the pipe diameters. Question is how. Q is 0. So delta S is also 0. For an ideal gas, okay, this is gonna be the specific gas constant, no? Kilojoule per kilogram Kelvin. Let's not do that. Wait. Let's not write it that way. N is equal to m over molar mass, no? M d sorry d over dt v d over dt m. R over m, that's going to be the specific gas constant. This one is this. This one is volumetric flow rate. Volumetric flow rate is equal to area times velocity. So P, technically P times area times velocity equals mass flow rate R specific times T. How will this help us? Sorry. Express in terms of so what are constants here? Velocity, this is the same, no? Obviously, R spec is also constant. Specific gas, constant, hence the word. What else? Isothermal process, so temperature is also constant. How about pressure? No? Pressure isn't. No, no, no. It's pressure and area that are not constant. So P1 A1 equals P2 A2. This is I think this is our first time not using the steam table, so our solution is pretty different, no? This is our approach. Since we're not using the steam table, we assume that the gas is ideal, and so we whip out these formulas. PV equals nRT. We know this for the mass flow rate and the volumetric flow rate. We know this as volumetric flow rate, this one as mass flow rate. We identify the constants and just the ones that vary, no? Since we're just looking for ratio, we don't have to know the information, the areas, no? Areas 1 and 2. So what are the conditions? Pressure 1 is 1,200 kPa, and then A1. P2 is 100 kPa, and then A2. A2 is the exit, no? A2 over A1 equals 1,200 over 100. Cancel the zeros, we have Can we recall the formulas earlier? AE over AI equals DE over DI squared equals PI over PE. Yes. Evidently, because this is the pressure inlet, 1,200, no? Inlet. We just proved this formula, how this one is equal to this. Because it's exactly this one. So twelve equals dE over dI raised to 2. And d raised to 1/2 on both sides. dE over dI. This is our ratio of diameter. Where is my calculator? 12. Essentially, square root of 12, which is 3.46. I think this is dimensionless, no? 464, sorry. Yeah. And that is our answer. We got it. This is one weird problem, number 5. We were able to get the concept for the most part. It's just we weren't used to the FLT and SLT not being the continuation in finding the actual answers, no? We were at a dead end. We identified enthalpy and entropy as 0, and we had to start anew with these formulas. So at this point, it's just important to memorize them, no? So yeah. What's next? So yeah, that's just specifically the nature of a throttle. It's isentropic. So these are all the assumptions. Next problem. Okay, so we have a condenser or heat exchanger. Heat exchanger, so we have, I think that's, yeah, that's the, so we have an inlet, outlet. So from the word exchanger, exchange of heat, no? Okay, so a condenser or heat exchanger brings 1 kilogram per second. We have a mass flow rate at 10 kPa from 300 degrees Celsius to saturated liquid at 10 kPa. The cooling is done by lake water. At 20 degrees Celsius. That returns to the lake at 30 degrees Celsius. For an insulated condenser, insulated, so there is no heat transfer, Q is 0. Required, find the flow rate. Flow rate. Okay. There is no accumulation mentioned, so the process is steady state. This is a thermodynamic device, so we would assume this is an open system. Assumptions: negligible kinetic energy, negligible potential energy. This is a condenser. It's not a pump, not a compressor, not a turbine, not an expander. So shaft work is equal to 0. Okay. Aside from that, Q is 0 at the adiabatic condition. Okay. What is our substance? Water, no? Water. Energy balance, delta H is Q plus W. Okay. Do we need an entropy balance? Process reversible or irreversibility, or is there isentropic efficiency information mentioned? No. So I think we're just gonna cap it at energy balance. We have a mass flow rate. We have condition for state 1. This is what? Water? Yeah. Ten kilopascal, 300 degrees Celsius. Three zero seven six point 51. Oh, okay. There is also a characteristic for condenser. Isobaric. It's isobaric. Wow. Every device is unique, no? Wow. It's not enough to just know the general process. Otherwise, you could be stuck, just like what's happening right now with me. Evidently, because the pressure was the same. Sorry, this is not right. 14. ₱20 na. So that's the answer. Wow. Wait. This is already correct, but I want to see this. Okay, so delta H equals 41.84. Okay, I think, sure. And then, in place, let's try to ignore this. In place of this, we have 41.84. Let's see what happens. 191.81 minus 3076.51 equals negative x times 41.84. Precisely. We were also able to get the same thing, 68.95 kilograms per second. Why did I try for an alternative solution? Wait. The lake water isn't necessarily saturated liquid. I'll end the video here. I need to check on this problem. But certainly the answer is correct.